ENVT 4402, Topic 11, Monte Carlo Simulation. Previously, we have seen that most decision makers are risk averse. This means that they would tend to select certain outcomes over risky outcomes with the same expected value. Risk aversion is like the discount rate. It is an important individual parameter and determines our attitude to various things such as savings, insurance, gambling, and other forms of risk. Decision makers often select between distributions of outcomes. For example, choices of fishing quota and pollution management determine the distribution of outcomes, such as fish stock, water quality in rivers, etc. Decision makers try to avoid extreme adverse events such as collapsing the fishery or damaging river ecosystem. However, outcomes are often uncertain and not in the control of a decision maker. So you have analyzed a model and come up with an optimal solution. The question is, how robust is it to assumptions about the parameters? For example, consider the fisheries growth parameter in a fisheries model. What happens if it varies within a range of values? There could be other parameters which influences the outcome of a model. To understand the impact of the values of parameters, Monte Carlo simulations is a very useful tool. Monte Carlo simulations are computer-driven experimental investigations in which certain parameters such as population means and standard deviations that are known a priori are used to generate random but plausible sample data. These generated data are then used to evaluate the sampling behavior of one or more statistics of interest. This process of generating and analyzing data is repeated over many iterations and differing conditions that are thought to influence the sampling behavior of the statistics of interest. Example through increasing sample size, mean differences, variability, etc. The organization of Monte Carlo simulations generally mirrors that of traditional research studies. We first have to generate a sample of data or gathered. Then we have to analyze if we're using one or more statistical methods and data operation. And finally, we have to summarize the results or statistics for dissemination. Hence, constructing Monte Carlo simulations is simply a matter of organizing a generate, analyze, summarize scheme so that particular data sets and analysis procedures can be emulated and studied over a wide number of random replications. There are usually 5 typical steps in a Monte Carlo simulation. We have to start from designing the factors of interest under study. Then we have to generate the data set. Then we have to analyze the relevant outputs. We have to summarize the outputs into using meta statistics or summary statistics. And then finally we have to report results. Let's consider a simple example of a fisheries. We are not using an optimization model here, it's just simulation model. What we have here is that we are interested in the profit from a fisheries. This profit is over multiple period of time. It's going from T1 to big T, capital T. The profit is calculated as the difference between total revenue and the total cost and multiplied by the discount factor. The total revenue is a function of the price of the fish or a unit of fish times the catch in period T. And the total cost is a product of the unit cost of fishing effort times the unit of efforts. So this profit function is subject to a population growth function, where the biomass in a period depends on the biomass in previous period, the growth parameter, carrying capacity, and catch. So xt plus 1 is the biomass in period t plus 1 minus biomass in the previous period xt, which is equal to the biological growth parameter gamma, biomass in period t, times 1 minus biomass in period t over the carrying capacity minus the catch, where catch is a function of catchability coefficient, biomass in period t, and the effort. And there are few other non-negative constraints. What is interesting for us to note is that what is exogenous, what is endogenous variables or parameters in this simple model. In other words, which variables are determined directly and indirectly within the model, which are given from outside. We can assume that the price of fish, cost of fishing effort, biological parameters such as catchability coefficient, growth parameter, carrying capacity, discount factor, they are all exogenously given, whereas effort and fish stocks and the biomass in each period, they are variables and are endogenously determined. Same as profit is also endogenously determined. Given this simple fisheries model, we can use a concept like comparative statistics to understand the impact of one or multiple exogenous parameters. Comparative statistics is the comparison of two different economic outcomes before and after a change in some underlying exogenous parameters. As a type of static analysis, it compares two different equilibrium states after the process of adjustment, if there is any. Let's have a look at this graph. Initially, we have an unit cost effort, or W equal to 20. So you had a total cost line of this one, the total cost. Let's assume that we have increased the unit cost by 20%, which means that now we have W equal to 24. So this has moved the total cost curve up, pivoted. But what is the impact on our profit and our optimal level of effort? So initially, with original cost of W equal to 20, we had this total cost line which intersected the total revenue line here, but the maximum difference was here. That is the total, where the total profit, net profit was maximized. So this is the point A, and the optimal level of effort was 80 here. Now we have increased the cost, so the total cost curve has moved towards left, pivoted towards left, which means that A is not optimal anymore. We have to shift slightly towards left, and B is our optimal level of effort, which is 76. So the effort decreased from 80 to 76. So that is the impact of increasing unit cost by 20% on the level of optimal effort. So what is the direction of change, positive or negative in this case? In this case, the effort has dropped, so it is negative. Is it expected to be monotonic, always positive or always negative? We do not know. It may be, maybe not. But in this particular case, because we are dealing with a very simple model, it is always monotonic. We can use the elasticity concept to measure responsiveness, as we have seen in previous classes. If the value of elasticity is greater than 1, we should assume that it is the outcome is responsive to the changes in the input, and it is positive and elastic. If elasticity is between 0 and 1, then it is positive, but the impact is very small. It's unresponsive. If elasticity is less than -1, then it is negative and elastic, again responsive. Whereas if it is elasticity is between 0 and -1, then it's negative and inelastic, unresponsive. When elasticity equal to 1 or -1, then it's unique elastic, which means that the percentage changes in input variable and the percentage changes in the output variable are the same. So that's why when we take the ratio, it is either 1 or -1. Let's have a look at more details into the Fisheries model. Here we are interested in a single parameter, fisheries growth parameter. We're assuming that instead of a fixed point estimates, we said that the gamma is distributed from a uniform distribution between 0.2 and 0.4. And this graph gives a distribution over 10,000 draws. If we estimate the area under these bars, we'll get a value of equal to 1. So we have simulated the fisheries model where we have varied the growth parameter randomly from 0.2 to 0.4. But at the same time, we have tested sensitivity of the model outcome towards 3 distinct quota or catch level. We assumed that quota there could be 3 levels: low catch, medium catch, and high catch. So in this particular graph, we have plotted the fish stock after 10 years period. What we observe is that when we allow high catch, that is indicated by the green line here, the fish stock has mostly collapsed after 10 years. This minus sign indicates the collapse. Fish stock remains positive only when the catch is either medium or low. So it is already showing some concern about the stock level after 10 years, especially with the high catch level. If we go into more details, in the top left graph, we have plotted the biomass in each period of time over 10 periods for each simulation under different quota. So these quotas, this is the low catch allowance or low quota, and this is going from 1 to 10 periods and then go to the second simulation to again 10 periods, etc. And then this is the medium level catch or quota, and this is the high level catch or quota. So you can clearly see that when there is a high level of catch or quota, the fish stocks collapsed more frequently. This can also be seen from here, where we have, when this is the high catch and this is the low and medium catch, and we have plotted only the fish stock after 10 years. You can see similar pattern either through frequency curve or through density curve. Interestingly, the present value of profit is not that influenced by the changes in the catch level or changes in the growth parameter. So what is the impact of a stock? It could be quite large, as we can see from the distribution. It's going from -77 to maximum 621 tons with a mean of 253. If we take a base value or a target value of 300, there are around 34% observations were below 300. So if that is our reference category, then in the 34% times the fisheries would fail. This shows the high sensitivity of the fish stock to catch level and the fisheries growth parameter. As I have shown before, the impact on profit is not that substantial. That means there are very few cases. I don't think there is any cases where the profit actually drops below zero or comes close to zero. So this is with a single parameter model, and how can we produce the results and present. Let's have a look at multiple parameters. Here we are using a particular fisheries, Hecate Strait sole data. It's in Canada. So we still are using our simple fisheries model, but we have calibrated using empirical data from these fisheries. So there are certain values of carrying capacity, catchability coefficient, intrinsic growth, price of fisheries, cost per unit effort per hour, and discount rate. So these are some observations where we have data from 1954 to 1979. What can we observe? We observe that the catch and effort are highly correlated, but at the same time catch per unit effort has dropped as the year progressed. So if we have a set of observations like this, as we have mentioned before, for Monte Carlo simulation or sensitivity analysis, it is very important to draw a sensible range for simulation. So when we have data like this, we can rely on deriving a suitable range based on this data, and often regression techniques are used to retrieve the sensible range or parameter values. So if it is a linear relationship, if we assume a linear relationship between m parameters and a data set of endpoints where there is a dependent variable y and m independent variables, then the linear regression can be written as follows. yi, that is the observation, ith observation of y, the dependent variable, which is a function of x1, x2, x3, and the betas are the coefficients that we estimated through linear regression, and epsilon is the error term. So given our fisheries data that we have just observed, we can model a Shepard's model, which is using the data, which is possible to express or rewrite as a linear regression model, where ut, the catch per unit effort, so catch per unit effort in future period t plus 1 divided by unit effort in current period, so this is the ratio, minus 1, which is equal to biological growth rate minus r divided by carrying capacity times catch times catchability, catch per unit effort minus q and effort. So given this linear formulation, it is possible to use some form of linear regression models to retrieve the parameter values. We assume the carrying capacity, which we fixed at 6,255. Then we can calculate the relationship between two growth parameters, gamma and the catchability coefficient theta, as we are most interested in these two. And so this is the mathematical code that we have used to plot or to provide input into the model. There is a negative relationship between catchability and the growth rate. The negative relationship indicates that the low growth rate is associated with high catchability. If you see the growth rate is going from 0 to 1, and whereas the catchability coefficient is going from 0 to 0.006. So this one is going up, whereas this one is going up on this side, but we see the higher values are over here. So that's why it's a negative relationship. So again, we can plot the model. We can generate final stock biomass, and in this case we assumed a 5 years period. We can see how the stock has varied or changed. So this is the distribution of stocks. We can also plot net present value or profit. What is interesting here is that if we go back to our previous slide, see that the final stock is higher when catch or quota limit is low. If you look at here, NPV or net present value of profit is higher, the catch is higher. It is possible to use stochastic dominance functions to see which level of quota is optimal or most preferred. But which value you should use, that's a question of your judgment. Do you use the optimal stock or the net present value? It depends on your objective function. So in summary, we have observed steps in a Monte Carlo simulation, talk a little bit about comparative statistics, and then we have explored a fisheries model for single parameter and multiple parameters. Thank you.